Isn't it a little ridiculous that we're expected to be software and systems design experts with just a few years of experience? And now we're gonna do it in the cloud, where most of us weren't even taught any of this in school, and there are now countless design frameworks or schools of thought out there. So where to get started? I get this question a lot as an AWS software architect, and my answer is always to start with the most fundamental and timeless principles. So in today's video, we will discuss the shifting responsibilities of a software engineer working in the cloud and how we can properly design complex distributed cloud applications. My name is Derick Chen, and this is BuildWithDC. The cost of writing application source code that codifies business logic is exponentially getting lower. As a software engineer today, it is no longer enough just to be able to write application code that interacts with another tier of the system. In the you build, you operate model in the cloud, with small and multidisciplinary teams, there are now additional expectations for software engineers as your tenure grows. Apart from delivering the implementation, the scope of responsibility extends also to the planning and design before the build phase, and also parts of the deployment and operating workflows with infrastructure as code. You are most likely already doing some of this work today. It's most likely that this responsibility will only expand. I will focus on the design work before the build phase today, because most college degrees for computer science don't cover this. We're somehow expected to pick this up as we go along, but it is such an opinionated and subjective discipline that is also constantly transforming. By design, I'm referring to the behavioral and performance design for a software system. Behavior is what the software system does, and performance is how well the solution does it. Some of you may see this as designing for the functional and non-functional requirements. It is important to be specific and have this separation so we can divide and conquer the complexity challenges that we have at hand. The earliest input to the design process is the product requirements. This may be in the form of user stories and epics from the product team. Then, we have to first design for the behaviors of the system, then focus on the performance optimization. Behavioral design converts business requirements into accurate workflows in the software, while performance design focuses on the best way to run these automated workflows that is least costly in terms of both money and time. The design process is a serialized two-step workflow. If done right, this should produce a blueprint for the implementation that can withstand the test of time and additional changes, helping us avoid expensive overhauls and rewrites. Most often than not, when you are dealing with a complex project, the design outcome is distributed. You already know that I will be talking about microservices, but before that, we need to linger a little bit on the notion of distributedness, and there's a myth we need to debunk. The reason why we distribute an entire software into separate components is to divide the underlying complexity into digestible working blocks for different teams, squads, and individual software engineers. The notion of distribution exists in a spectrum, but typically we can group them into the centralized, decentralized, and distributed types of architecture with increasing degree of distribution. The concept of microservices belong to the decentralized group of architecture. And by microservices, I mean software components that are each complex enough to be built and delivered by at least a team of 3. If your service breakdown is any finer than that, then you are in the realm of nanoservices, or the distributed group of architecture. This is most likely not ideal unless there are specific business or technical constraints that you need to meet with small scope in your software components. The reason is that this typically adds a lot of integration overheads and complexity, both in the software artifacts, the APIs, events, hardware operations, etc., and also in the process. The process of collaborating with more people and even potentially with different teams too. And here's the myth that I mentioned earlier. Monoliths are bad. By now, our industry has already given centralized architecture, the monoliths, such a bad name that it can hardly ever come back from. But centralized architecture are not necessarily bad. In many cases, such monoliths can extract more performance gains, especially in latency, and work much better if the computation required is not meant to be distributed over a network. So, is there a right and wrong for the level of distribution? Yes, there is. Software architecture design may be opinionated and subjective, but there is a measure of correctness. A good distribution is determined by the behavior and performance requirements of the system. Based on the requirements, the architecture must follow the concepts of high cohesion and loose coupling between software components. High cohesion and loose coupling are the fundamental principles of software design that promote maintainability, scalability, and clarity in distributed systems. Cohesion measures how closely related and focused are the responsibilities of a module, class, or function. A highly cohesive module performs a well-defined set of tasks that are closely related to each other. Consider a class with functions that each has a single, focused responsibility and are related to each other conceptually. In the shopping cart class for an e-commerce application, there are most likely functions to calculate the total price and also to add and remove items. It would be strange to place these functions anywhere outside this class, since they are specific to the concept of shopping cart and there's little likelihood that we'll reuse them anywhere else. On the other hand, coupling measures the degree of dependency between modules, classes, and functions. Loose coupling means that components are minimally dependent on each other, reducing the impact of changes and disruption from one module to another. An example will be an event-driven system, where the point of dependency is reduced to the agreed-upon event definition. The logical implementation of the suppliers and consumers of these events can be modified independently without cascading impacts as long as the event structure remains agreeable. The first step of our design process, behavior design, can already give us a strong signal of how to decompose requirements into smaller modules and services. Only in scenarios with stringent performance requirements or technical bottlenecks, then the performance design step may influence the breakdown of our service boundaries. These principles of high cohesion and loose coupling are not only applicable in the back-end application design. These principles also naturally extend to the front end with micro front ends and into the infrastructure as code layers of your software architecture. The result is independent software deployment units that can be iterated on in parallel with minimal mutual dependency and conflicts. In a complex scenario where multiple teams are working together, this ensures a good level of productivity across the entire engineering organization. If done right, the overall architecture will lead to an improvement of the DORA matrix. Frequency of deployment, lead time for changes, change fail rate, and mean time to restore. This allows us to build faster and better, and also enhance the adaptiveness of our software systems. In summary, we explored the evolving role of software engineers in a world where writing application code is becoming increasingly accessible. Beyond implementation delivery, modern software engineers are now also expected to contribute to the planning and designing of the software solution in the cloud. The software design process involves two key steps: behavioral design, translating business requirements into accurate workflows, and performance design, optimizing these workflows for cost efficiency in both time and resources. The right level of system distribution depends on the system's behavior and performance requirements. Key principles like high cohesion and loose coupling are always essential for maintainability, scalability, and clarity in the backend, front end, and as well as the infrastructure as code layer of your software system. Finally, with good design, we can improve the DORA matrix, helping teams build more adaptive software systems, deploy faster, and also recover quickly. In the next few videos, we will have an example of the behavior and performance design process, where you can see how everything works together in reality. We will start with a list of user stories and design an adaptive distributed cloud application. I hope you have enjoyed this video on distributed software architecture in the cloud and found insights that you can put into practice for whatever you are building next. Remember to like, comment, and share this video. And if you want to know more secrets of designing highly performant software architecture, remember to subscribe to the channel. My name is Derick Chen. Thanks for watching, and we'll see you in the next video.